Imagine a machine that takes raw fuel and turns it into the electricity powering your home. That is the job of a gas turboset. At its core, this system is a master of energy conversion. It starts with the chemical energy locked inside fuel and, through a series of precise mechanical steps, transforms it into high-voltage electricity ready to be sent across the power grid. The process begins in the combustion chamber, where fuel is ignited to release intense heat. This thermal energy is then funneled into the turbine, where the real magic happens. As the heat hits the turbine blades, it's converted first into kinetic energy and then into mechanical energy, spinning a massive central shaft. Finally, that spinning motion reaches a generator, which uses the principle of induction to turn mechanical force into the electrical current we use every day. How do we get that gas to move fast enough to turn a heavy turbine? It comes down to thermodynamics. By using specifically designed nozzles, the system forces the high-pressure combustion gas to expand. As the pressure drops, the velocity skyrockets. This creates a powerful torque on the moving blades. To track this energy, engineers look at enthalpy, a combination of pressure, temperature, and volume, to ensure the gas is performing at its peak. Efficiency is the name of the game. By arranging the turbine blades in a precise sequence, the system extracts as much mechanical energy as possible from the gas. This cycle continues until the gas pressure drops to almost atmospheric levels. At that point, the spent gas is discharged. Even though the pressure is gone, the exhaust is still quite hot, marking the final stage of the turbine's journey before the air returns to the atmosphere. To achieve high efficiency, engineers aim for a high turbine inlet temperature, TIT. However, this leaves us with a very hot exhaust gas, known as the temperature after turbine, TAT. Instead of wasting that heat, a heat recovery steam generator, HRSG, is added to the system. This secondary unit captures the exhaust heat to boil water into steam, which can then power a separate turboset for extra electricity or even fuel a desalination plant. This, combined approach ensures we get the most out of every drop of fuel. To master heat conversion, we have to talk about entropy. Think of entropy as the rulebook for heat. It tells us three things. First, heat always flows from hot to cold. Second, heat can never be converted into another energy form with 100% efficiency. And third, energy losses are inevitable in the real world. By tracking entropy alongside temperature, engineers can create a visual map, a heat diagram, that shows exactly how much energy is actually available to be turned into mechanical power. A standard gas turbine process is often visualized as a 4-point loop. It starts at point 1 to 2, where air is squeezed inside a compressor. Then, from point 2 to 3, combustion occurs at high pressure, adding massive heat from the fuel. From point 3 to 4, that high-energy gas expands through the turbine to create motion. Finally, at point 4 and back to 1, the exhaust is discharged at low pressure. The area inside this 1, 2, 3, 4 loop on a graph represents the total heat successfully converted into mechanical energy. Before any energy can be produced, the turbine needs a steady supply of air. Interestingly, no energy is added to the air until it hits the very first row of compressor blades. To get the air moving, the compressor actually pulls air away from the intake, creating a drop in local pressure. This allows atmospheric pressure to push fresh, filtered air through the intake manifold to fill the gap. Because the pressure is constantly falling as air moves inward, engineers have to be incredibly careful with the design of the journal bearings. If a seal fails, oil could be sucked into the airstream and contaminate the entire system. The heart of the machine is the axial flow turbine. It gets its name from a simple fact: the combustion gas flows parallel to the main axis of the turbine shaft. To convert heat into motion, the turbine uses two specific types of blades. First, there are fixed blades, also called stators or vanes, attached to the outer casing. Their job isn't to spin, but to act as guides, directing the hot gas at the perfect angle onto the second set, the moving blades. These moving blades, known as rotors or buckets, are mounted on the spinning core and deliver mechanical power directly to the rotor shaft. When you combine one row of fixed vanes with one row of moving buckets, you create what engineers call a turbine stage. This is the exact room where heat officially becomes mechanical work. To visualize this perfectly, experts use velocity triangles, which map out exactly how the speed and direction of the gas change as it passes through the blades, ensuring maximum power is captured at every stage. While heat is the energy source, pressure is the catalyst, and that pressure is provided entirely by the compressor. Mounted on the same shaft as the turbine, the compressor works in the exact opposite way. Its rotating blades accelerate the air to high speeds, and then fixed vanes convert that kinetic energy into pressure. Because it is physically harder to squeeze air than it is to let it expand, you'll notice that a gas turbine usually has many more compressor stages than turbine stages to get the job done. Running a compressor isn't always smooth sailing. It is incredibly difficult to match the mass flow, the actual volume of air, between the compressor and the turbine at every speed. If they aren't matched perfectly, especially during startup or shutdown, the compressor can surge or stall. To prevent this, engineers equip the system with blow-off valves. These valves stay open during low speeds to vent excess air, and only snap shut once the shaft reaches its rated speed and the airflows are finally in sync. Just like the turbine, the compressor is organized into stages consisting of moving buckets and fixed vanes. However, in this stage, the blades act as divergent nozzles. As the air passes through, it actually decelerates. This controlled slowing results in three critical changes: an increase in fluid pressure, an increase in temperature, and a decrease in volume. This transformation from mechanical rotation into pneumatic energy is what prepares the air for the combustion chamber. We finally arrive at the combustion chamber, the heart of the engine's energy release. This is where the chemical energy of the fuel is unlocked and transferred as intense heat into the compressed air. This reaction triggers three critical transformations. First, the air's specific energy, or enthalpy, skyrockets. Second, its temperature is driven to its absolute peak values. And finally, the air chemically converts into high-energy combustion gas. It is this superheated, high-pressure gas that provides the raw force needed to drive the turbine and generate massive amounts of power. Inside the combustion chamber, the process happens under constant pressure, known in thermodynamics as an isobaric thermal process. To get the most efficiency out of the turbine, we want the highest possible inlet temperature. However, there's a catch: the hotter we burn, the more we test the limits of the materials. Engineering this means balancing high-performance power with the lifespan of the hot gas components that have to survive that intense heat. Modern turbines are designed to be as green as possible using environmental EV burners. These are typically found in silo or annular combustors. Unlike old-school burners, these EV systems achieve two major goals. They significantly boost turbine efficiency while slashing harmful emissions, specifically nitrogen oxides, or NOx. It's a win-win for both power output and the planet. The magic of an EV burner lies in how it mixes fuel and air. Compressed air is fed into a double-cone burner to create a perfectly balanced, lean mixture. The shape of the burner induces a vortex flow that essentially breaks down at the exit, forming a recirculation zone. This zone is critical. It stabilizes the flame in free space, keeping the fire from touching the combustor walls. This prevents the metal from melting and ensures a clean, steady burn in a single, low-temperature flame ring. Why do engineers prefer an annular combustor? It comes down to balance. By distributing burners evenly in a ring, the gas flow and temperature distribution become much more uniform. This design allows for a significantly shorter gas path, meaning there's less material that needs to be cooled. With a lower demand for cooling air, more air is available for flame dilution, which directly reduces those pesky NOx emissions. Plus, its compact, simpler layout makes it easier and cheaper to install within a single enclosure. The EV burner itself is a masterclass in elementary design. It's shaped like two half cones that are slightly offset to create two long slots running their full length. This dual-fuel burner can handle both gaseous and liquid fuels with ease. As combustion air enters through those slots, gaseous fuel is injected radially through a series of fine holes along the edges. This setup ensures the fuel and air are intensively mixed before they even reach the flame. The real breakthrough here is the use of excess air. By designing the burner to run lean, the flame temperature is kept roughly 500 degrees Celsius lower than a conventional burner. Since the formation of NOx depends mostly on high temperatures and how long the gas stays in the chamber, this temperature drop is a game changer. By combining a lower flame temperature with a shorter residence time, the EV burner achieves incredibly low emission concentrations without sacrificing power. When we look at the big picture, the transition to environmental combustion using EV burners is a massive leap forward for power plant technology. By creating an extremely homogeneous fuel and air mixture, these systems ensure that every ounce of energy is utilized through thorough combustion. Most importantly, This precision effectively inhibits NOx emissions, proving that we can meet the world's massive demand for electricity while still prioritizing environmental health and air quality. The final transformation, from mechanical spin to electrical power, is made possible by the principle of electromagnetic induction. To generate electricity, you need three things: a strong magnetic field, an electric coil, and relative movement between the two. In our turboset, the rotor of the generator acts as the magnet, while the stator winding acts as the coil. As the gas turbine spins the rotor at high speeds, it creates a moving magnetic field that induces a voltage at the stator terminals, creating the current that flows to the grid. To ensure the electricity we produce is stable, we have to control the strength of that magnetic field. This is done through an excitation winding on the rotor. By feeding a specific amount of direct current, known as excitation current, into this winding, we can vary the induced voltage and stabilize it instantly. This current is delivered by an independent source called an exciter. In modern plants, you'll usually find either a static exciter or a brushless exciter, which uses rotating diodes to transfer power without the need for physical contact. To keep the generator running without the wear and tear of physical contact, modern systems use a brushless exciter. Think of this as a mini generator attached to the main shaft. Unlike the main generator, where the magnet spins inside a coil, the exciter often works in reverse. The magnet is fixed, and the electric coil rotates. This allows the system to generate the necessary excitation current internally, which is then rectified by rotating diodes and fed directly into the main generator's rotor. The brain of this entire electrical operation is the automatic voltage regulator, AVR. The AVR constantly monitors the generator's outlet voltage and compares it against a precise, set value. If there's even a tiny discrepancy, the AVR triggers a command to adjust the excitation current. This adjustment loop continues in real time until the difference between the actual output and the set value reaches a pre-established, safe level, ensuring that the electricity sent to the grid is always of the highest quality. One of the most surprising facts about a gas turbine is how it actually starts. Because it's a combustion machine, it needs a shove to get going, much like a car's starter motor. But in a massive gas turboset, the generator itself actually acts as the starting motor. Using an external power source, the generator is temporarily used to spin the turbine shaft up to a speed where combustion can take over. Once the fire is lit and the turbine is self-sustaining, the machine switches roles, and the motor becomes a generator once again. Large gas turbines aren't self-starting. They need an external push to reach a speed where combustion can take over. To do this, engineers apply a clever trick. They use the generator as an electric motor. An electric motor has the same basic components as a generator but functions in the opposite direction, converting electrical energy back into mechanical torque. By applying a voltage to the stator winding and an excitation current to the rotor magnet, the shaft begins to turn. This starting process is managed by the static starting device, SSD. Fed with energy directly from the grid, the SSD has two main jobs. It supplies a variable frequency voltage to the stator winding and delivers excitation current directly to the rotor. By carefully varying the frequency of that applied voltage, the SSD can precisely control the rotational speed of the rotor, accelerating the entire turboset from a standstill. Once the turbine reaches a specific speed and the combustion process becomes stable, the requirement for a starting motor vanishes. At this precise moment, the SSD is disconnected, and the gas turbine begins to accelerate by itself under the power of combustion. The machine then transitions from consuming grid power to supplying it, closing the loop on one of the most complex mechanical startup sequences in modern engineering. That brings us to the end of our look at the gas turbine process. We've tracked energy from the first flame to the final electrical pulse sent to the grid. Thank you for watching. If you enjoyed this breakdown of enthalpy, entropy, and turbine physics, please like and subscribe. In our next video, we're moving from theory to hardware. We will explore the major components of the gas turboset, diving deep into the rotor, the specialized casings, and the heavy-duty engineering that makes this power possible. See you then.